Hello class, and welcome to the first week of content. We're going to be diving into data this week. I'm going to create a series of 3 videos, each one talking about a different introductory topic to data. And this first one, we're really going to get into the nuts and bolts of what data is and how it's structured. This is going to be very important as we continue to build upon our skills throughout this course. So I really want to make sure that in this first module, in the second module, I should say, but really early on in this course, we're going to be hitting home the key principles and key elements that we need to keep in mind when working with data. So I have a few slides that I want to walk through and just touch on the main points. So let me bring that up here. And so I really want to start with kind of an introduction to data, and the first series of videos we're going to be walking through these questions. What is data and how can we describe it? What are the ways that we can describe data? What types of associations and variables can our data have? Or what type of associations can variables with inside of our data have? So we're going to be looking at different associations between numerical variables, categorical variables, and how we can display and view that information and create some associations, create some visuals from our data. And then lastly, what are some data collection principles? What are the basics on how we collect data for a statistical experiment or an analysis? So in this first part, what is data? How can we describe it? So I really like this quote from the book. And I promise there's not going to be too much of me just reading off of a slide, but this is the main one that I really want to look at. So, you can read through this entire quote, but I really like how it describes how scientists are seeking to answer questions. To answer those questions, they need to observe different aspects in the real world or from an experiment, and then they're going to store those observations into a data set. We are then going to study that data set and then create some sort of analysis or findings or insight from that data set. So really this course is all about how do we collect data, how do we create some experiments or some observational studies that collect high quality data, how do we analyze that data and that information, and then ultimately how do we draw conclusions from that. So this first part is going to be, before we even get into collecting and analyzing data, what is data? So we explored this data set in the first class, and it shows it shows a structure of data called a data frame. And this structure is what we're going to be using throughout the course to explore our data set and to use and make inferences about our data set. There are going to be some other types of structures, mainly lists, but we'll get to that a little bit later when we're working with R. But yeah, I want you to really understand and think about the term data frame, because that's going to be the main structure of data when we're working with it in this class. A lot of people just associate data as a data frame. Data can take multiple different forms, but when we're working with data in this class, it's going to be mainly in the form of a data frame. So we can kind of use those terms interchangeably, but just know that data does not always have to be in a data frame or a tabular format. And so what do I mean by a data frame? So this is how data is structured. It's called a data, or it can also be called a data matrix. But why it's called a data frame is because it resembles a window frame. On the top of our window, we have our variables. So you can see those variables as the columns in our data set. And that will allow us to kind of see different aspects of a particular observation. And so our rows are our actual observations in the data set. So those are going to be really important for understanding what are we actually observing. Is it a survey? Is every row a different survey response? Are we observing in our data set earlier, it was a data set about different states. So each state is a different observation in our data set. But ultimately, when we're working with data, it's going to be in the form of a data frame. And so when you hear that term in R, because a lot of what we're going to be working with is data frames in R, just know that just means a table. There's nothing special about it. It's just a table, but in kind of R speak. So I want us all to think about a data frame or data as if it were a sentence. So every sentence has a subject and a predicate, I believe is the term. But the predicate is usually doing something to describe the subject of the sentence or explain or put context around the subject of the sentence. So the subject is going to be our observations in our data set. Every row is a new subject, and every variable is an adjective. Those adjectives are trying to describe the observation in our data set. So when we look through, we're going to see observations. So in this case, when we're looking at this data set right here, it's going to be states, and then every variable is going to do something to describe that state, whether it's population, income, illiteracy rate, so on. And these variables in our data set can take multiple forms. So it can be numbers like population, or it can be characters like state dot division. So how do we classify the different types of variables that we can see in our data frame? Well, there's two main classifications. There's categorical and there's numerical. The main takeaway I want you to have from this is categorical categorizes a row in 1 to n number of categories, n being kind of like an integer that can be between 1 and infinity. So it can take the form of numbers, so we can have numbers in a categorical variable, but generally this is going to be characters, it's going to be words. So a good example of a categorical variable is region. So we have north, south, east, and west. That can be, so a column can be region, and that can be a way that we categorize the data in our data frame. Another type of variable is numerical. So we have different numerical values for income, let's say. So there's different types of categorical and numerical variables. So the next slide gets into the specifics. The key ones I wanted to point to, actually they're all key, so I'm going to hit on all of them. The one that's a little bit different from the rest is the unique identifier. So we can think of things as like a person's social security number or their student ID, or if it could be your email. If you are, let's say, logging in to, you're logging into a website and you need a username and a password, your username is going to be the unique identifier for that website. So if a company wants to look up anything about your user profile, they'll generally use your email as the unique identifier so they can look up information on your user profile. Now, you wouldn't use an email or a SSN or a student ID to do any deeper analysis. This is just a value that allows us to look up a specific record, a specific row in a data set. So we don't really need to use this in any particular way for our analyses. One thing that a unique identifier can be done or can be used for is a counting mechanism. So we might want to count how many individuals we have in a certain category. We can count the unique identifier in a data set to do that. But we'll get into that in a little bit later when we're talking about data visualization. So for categorical, the other two types of categorical variables are nominal and ordinal. Now, nominal is the general all-purpose categorical variable that we looked at before with north, south, east, and west. Ordinal would be something that takes, there's some order to our categories. So we could have, let's say that we have different users on a product or a website, and we categorize them as either top users, mid-tier users, or rarely used. So we could have a 1, 2, or a 3 that categorizes that user's activity, and that would be an ordinal categorical variable. Now, even though it takes the form of 1, 2, and 3, we wouldn't be able to aggregate those 1, 2s, and 3s because they're specific categories. So they would be a categorical variable even though it has a number, but it would be an ordinal categorical variable as opposed to a nominal. For our numerical variables, there's two different types. We have continuous and discrete. The way that I like to differentiate these two is continuous is we can think of a number line. So let's say we have a number line from 0 to 100,000, and you take your pen and you put your pen on any point on that number line. Depending on how precise our measurements can be, your pen's going to fall on a specific point on that number line, and it can fall anywhere on that number line. And so things like income, or let's say miles driven in a year, or let's say like heart rate, or population, these are all values that can fall really anywhere on a number line. We can use something, we can measure a person's heart rate, we can measure distance traveled. So that's going to be a continuous number. If we're counting something, like we're counting the number of people in a household or cars in a household, or how many internet connected devices does a person own, or how many friends does a person have, how many family members does a person have. These are discrete numerical variables because we can't have a half or we can't have a third of something. We have to count each individual item. So there's no way that we can measure. We can't measure the amount of people in a household. We can only really count people in a household. Now, it gets a little hairy when we talk about population because we have such large numbers. So there could be an argument that population is a discrete variable, but I would generally like to think of population as a continuous variable, even though technically we can count everybody in a population. Or generally, because it's such a large number, we're generally going to think about it as a continuous variable. But it is one of those that kind of toes the line in between the two. Okay. And so the last thing that I want to get to in this section is talking about there's certain variables in our data frame that we're going to call explanatory variables. And there's certain variables that we're going to talk about as response variables. So let's actually go back up to our data frame here. And we might be tasked from the Department of Health to look at different aspects, different variables about each state. And we're trying to understand what has an impact to life expectancy. That's the most important variable that the Department of Health wants to understand. So we are going to create an analysis that looks at what variables are associated or explain life expectancy. So we could look at something like income or high school graduation rate or the murder rate, and we could use each of those variables to explain what is the expected life expectancy for that state. So we could create create a linear correlation. We could create some visuals all around explaining life expectancy. So we can assume that as income increases, or as high school graduation rate increases, or as a murder rate decreases, our life expectancy would increase. So if we go back to this slide, we're really trying to figure out what variable explains our response variable. Now, there is a little kind of a hidden aspect that sometimes we're not going to realize when we're talking about explanatory and response variables. And what I mean by that is there's sometimes going to be a confounding variable. So there's a variable that it looks like explains another variable, but truly there is a confounding variable that is just interacting with both. So there's a classic example that I like to talk about, and it's this community is doing research. It wants to, it thinks it has a problem with the number of people that are drowning every year in the local pond or the local lake or the local ocean. And it does this huge data collection process, and it tries to understand, what months, at what times are people, or what impacts people the most to that end up drowning in a particular time frame. And one thing they find is that ice cream sales, so let's just draw that here. Ice cream sales seems to explain the drowning rate. So if we draw a linear correlation, we'd see something where as ice cream sales increases, so does our drowning rate. Now, it seems a little dubious. And actually, I'm not sure that's how you spell drowning, but we're just going to say that's how you spell drowning. It seems a little dubious, but it's in the data. It's true. It's a fact. Ice cream sales increase along with the drowning rate. So how do we make sense of this phenomenon? Well, as you probably have assumed, there's a confounding variable that's impacting them both, and that is going to be the temperature. So as temperature increases, more people want to go outside, they want to get an ice cream so that they can cool themselves off, or they're also going to go swimming to cool themselves off. So it's really the temperature that is going to be predictive of ice cream sales and the drowning rate. But we might not intuitively see that at first, given our data set. So this is a pretty obvious example so that we can make a clear distinction of ice cream sales isn't actually causing people to drown. But depending on the data set that you have, you might find these correlations and these relationships that are actually being caused by a different confounding variable. Now, it's not always a bad thing. If you have a data set and you see a relationship between, let's say, ice cream sales and the drowning rate, that could be a useful thing to know if we want to try to predict the drowning rate, or we want to try to predict something in our response variable, because we might not always actually have temperature. That might not be a variable that we have access to in our data set. So having ice cream sales is actually really helpful to predict the drowning rate, but it does not mean that these two are related to one another or that one causes the other. That's really important to remember. And so here's a definition. So our explanatory variable is a variable that might affect the outcome of what we were trying to predict in our statistical study. It's a variable that explains our response variable. And so our response variable is the outcome. What are we trying to analyze in our statistical study? And a confounding variable is a variable that influences both the explanatory and the response variable, but it might not be known or it might not be able to be measured. So we might not be, in the hypothetical example, let's say that we haven't invented thermometers yet. So we don't really have a way of measuring the temperature. We just know that these two variables are related. So if we want to try to predict drownings, then we can use ice cream sales as kind of a proxy to predict drownings. So that's it for section 1. I hope you've all enjoyed the video, and I'll catch you on the second section of this video where we're talking about what types of associations can variables have in our data set. All right, thank you.